Hello, I'm Jonghyun at Iowa State University. In a video lecture given by Professor Doug Masson at Tufts University, he gave a good overview on his thoughts on physical sciences research in space for the next 10 years. As part of his vision, he mentioned the measurement of thermophysical properties of molten metals and ceramics. In this video, I'll talk more about why it is important to have accurate thermophysical properties for the successful fabrication of metal parts in space and on Earth. We are part of the ISS EML project. Now we are working on the ELF project. We are studying solidification, glass formation, quasi-crystal formation, and interfacial phenomena of various metals and oxides using both EML and ELF facilities aboard the International Space Station. Measuring accurate thermophysical properties is not only an important task itself, but provides critical parameters for the studies I just mentioned. For instance, we are interested in the influence of the melt convection and the phase selection of various alloys during solidification. In order to characterize the flow in a molten sample, we developed and experimentally validated computational fluid dynamic models which require thermophysical properties such as density, viscosity, and surface tension. Here is how we measure density, viscosity, and surface tension in a molten metal using ESL. Once we levitate a charged metal sample in an electric field formed by a pair of vertical aligned electrodes, we heat up and melt the sample by applying a heating laser. After the desired temperature is reached, we turn off the laser and the sample cools down and solidifies. During this thermal cycle, we track the sample temperature by optical pyrometry and capture the silhouette of the sample using a high-speed camera. By combining the volume data calculated from the video data and temperature gives us the density as a function of temperature. Viscosity and surface tension are measured by a technique called oscillating droplet method. In this case, we excite the molten sample and let the sample dampen freely at a desired temperature. Again, we capture the oscillation damping behavior using the high-speed camera. Analyzing this video gives the oscillation frequency and damping time from which we can calculate the surface tension and viscosity respectively. Now I'm going to explain how these thermophysical properties are related to in-space manufacturing. For the success of long-duration exploration missions, sustainable missions, and flexible missions, we need the capabilities listed here. We should be able to repair facilities or equipment on site, and we cannot depend on resupply from Earth for every part. Also, we need to recycle materials. All of these are directly related to cost. Sometimes, even if we can afford the cost, time could matter. You can imagine how long it would take to deliver a part from Earth to Mars. So ISM should enable some deep space exploration missions which are currently considered impossible or unrealistic. Metals are one of the main materials that serve space exploration, and research on metal welding, joining, or additive manufacturing in space have been actively performed. Metal additive manufacturing is a complicated process which requires knowledge from many different disciplines. It is basically high-temperature metal processing, which involves melting and solidification. Although we have seen some success stories of using metal additive manufacturing, there are still many issues that need to be addressed, as we can see from this figure. We need knowledge and technologies related to solidification, thermophysical properties, heat and mass transport. And finally, we need to be able to evaluate additive parts before any serious field applications. In order to address the issue I just mentioned, there have been national level efforts. National labs and many academic institutions join these efforts. What they're aiming at is to develop multi-scale physics-based numerical models which can simulate the additive manufacturing process from materials melting, solidification, phase transformation during cooling, and the final microstructure, which in turn can give the properties of the fabricated part. One of the reasons why numerical approaches were adopted was that the metal additive manufacturing processes are not easy to study solely by experiment because melting and solidification, of course, in a micrometer scale and in a millisecond scale. For the case of in-space manufacturing, the role of numerical modeling could be even more important, as experimental studies are very limited. The result from the melting and solidification model will be input into the microstructure model. We observed that the convection in the melt significantly altered the solidification behavior and its resulting microstructure, as we can see from the figure on the left. In this figure, the upper and lower regions underwent different phase selection processes during solidification and had quite different grain structures. In this process, the melt convection played a crucial role. Therefore, it is of critical importance to have a sound flow model to simulate melt and solidification, which requires accurate thermophysical properties. This is more important when you are developing new alloys for a specific in-space additive manufacturing process. Unfortunately, the thermophysical properties of new alloys are typically not available. What is usually done is to use the thermophysical properties of the alloys in similar compositions to guess the thermophysical properties using a simple method such as the rule of mixtures, or sometimes to use a constant thermophysical property value at the melting point, ignoring its temperature dependence. This could lead to a considerable error in the simulated results. Here's one example. These two plots show how the viscosity and surface tension of metal alloys vary as a function of temperature and composition. The figure on the left shows the viscosity of iron boron, which can vary by 100% depending on the composition and the temperature. If this variation in viscosity is not fully considered, the result of the multiple flow model could be misleading. The equation in the plot is for the Reynolds number, which shows the relative dominance between the inertia and the viscosity. If the Reynolds number is low, the flow is called laminar. You can imagine how honey flows as an extreme case. If the Reynolds number is high, inertia term dominates and the flow is turbulent. You can imagine a fast and violent flow. The flow of a molten metal is also characterized by this Reynolds number, which is a strong function of viscosity. Depending on the value of the Reynolds number, you may have to choose between a laminar model or a turbulent model. If your viscosity value is quite off from the true value in your simulation, you will have the Reynolds number which is also quite off from the true value, and your predicted melt convection could be wrong. The surface tension of aluminum nickel alloys also show nonlinear variation as a function of composition as shown in the figure on the right. Small difference in surface tension could result in the prediction of totally different convection conditions in a micrometer scale multiple of additive manufacturing, in which surface tension driven flow dominates due to the high surface-to-volume ratio. The temperature and composition dependence of thermophysical properties must be considered in the multiple flow simulations. Otherwise, we are putting the first button wrong. Mass evaporation also matters. Even though you started with your desired composition, the final composition of an additive part you just fabricated could be off by a few percent because of selective evaporation of elements with higher vapor pressure. Difference in composition by a few percent could lead to considerable loss in properties of interest. In our experiments with iron-cobalt alloys, the concentration of iron reduced by 2 to 4 weight% during one melt cycle in the vacuum. For most additive manufacturing processes, melt and solidification occurs in an inert gas environment, which suppresses mass evaporation by orders of magnitude compared to the evaporation in vacuum condition. However, the maximum temperature could go up to 3000 Kelvin for the case of additive manufacturing, and this often causes mass evaporation, which is large enough to shift the composition. The experimental data on such selective evaporation must be acquired in order to effectively and efficiently design and develop new metal alloys and eventually fabricate a metal part of a desired properties for a specific in-space additive manufacturing process. This presentation focuses on the significance of having accurate thermophysical properties, including selective evaporation of new metallic alloys developed for welding, joining, and additive manufacturing both in space and on Earth. On national level, large investment is being made to develop numerical framework which predicts melting, solidification, phase transformation, and final properties of metallic alloys during additive manufacturing. This modeling technique can directly be applied to in-space manufacturing. The multiple convection must be modeled as accurate as possible, as it is the first button which gives the initial microstructure. The soundness of a computational fluid dynamic model of a multiple depends heavily on the soundness of the thermophysical properties of molten metal. However, not much attention has been paid to establishing the database of thermophysical properties or sharing the database among the community. Establishing thermophysical properties database takes time. It is the really time to start. As the thermophysical property data is being accumulated in the database, they will have large impacts on our sciences, technologies, and industry, which is related to advanced manufacturing of metals in space and on Earth. Thank you for your attention.